In this video, I'm going to go through two bending questions that are both based on engineering mechanics by Neil Haj, and they're both based on past HSC questions. They're both reminiscent of HSC questions. I have some critiques, particularly this one, but we'll talk about how we're going to approach it. So in this question here, we have to find the allowable load given a permissible stress. So we're not instead of finding the stress, instead what they've told us is they've just told us the load, and we're going to find the stress. Now that load, that stress that we're allowed for this material is I lost the page. 65 MPa. Now, because we've talked about factors of safety, that might mean that the material can actually hold about 130 megapascals. So maybe something like aluminium, if it was made out of a solid block of aluminium. Probably unlikely. I wouldn't have chosen this value. I would have chosen a much lower value. I think a value of 5 or 6 MPa would be a better thing if we're talking about something that looks like it's probably made out of timber. But let's run with it. Maybe this is a really highly engineered timber. Now, I know a lot of students really struggle with this. Now, when I've taught this before, but it's not a simple question, but we're going to work backwards. So what we're going to do is we're going to say, first of all, we know the rule is that the bending stress, the rule is my over I, which is, I'll say each of the parts. The bending stress, which is measured in megapascals, is equal to the maximum bending moment, or the bending moment at the location, but we're typically interested in the maximum, multiplied by the distance from the neutral axis to the extreme fibre. Now, it's important to remember there's two distances from the neutral axis to the extreme fibre. Most of the time, in the symmetrical section, that doesn't matter, right? We just take one of them. And then dividing by IXX, right? Which they're provided just as I, which is the second moment of area, or the moment of inertia is another name for that. Okay, so in our case here, let's start by saying, well, what is the formula for finding the maximum bending moment? Well, what we can say is that at this location, the bending moment on this side, right, is going to be F on 2, half of F, multiplied by half of 6, right? I think we're 6 on 3, anyway, half of 6. And then the opposite side, it's going to be the same thing. So they're going to cancel each other out. So what that means is that in our case, right, what we could normally do is we could just say this is L. Let's use L as an example, right? What we'd normally call, let's say, this bending moment is going to equal to F times L, F on 2 times L on 2, which is the same as FL on 4. That's the same thing. Okay, so I'm just going to use that formula for the moment. Now that only works, FL on 4 only works only if it's simple symmetrical. Yeah? So, that's how we're going to find the bending moment. The next thing we need to know is what is the Y value? Well, in this case, the Y value is going to, Y bar is going to equal, so sometimes written like this, Y bar, is the distance from the neutral axis to the extreme fibre. So in this case, the neutral axis is there. We've got Y2, is the top in compression, or is the top is the top being squashed, or is the top being stretched? Yeah, so it's in compression, and then the bottom is the distance from the neutral axis to the compressive fibre, and so when I say fibre, I mean literally the molecules, the piece of timber at the extreme end. Yeah, so it's a difference from the neutral axis, the area that's not in tension or in compression, which usually for a symmetrical section is in the middle, and we're measuring the distance from that area that's under no stress to the area that's under maximum stress. And when I say area, I mean like literally the molecules of timber that are closest to the edge. So in this case, it's going to be equal to both YC equals YT, which is equal to D on 2, which is equal to 120 on 2. So we can say that Y equals 60, and we're measuring that in millimeters. Because we're using grease units, we go together like megapascals and millimeters squared. Okay, IXX. When I say IXX, what that means is second moment of area can be measured in two directions. It can be measured in the X direction or the Y direction. We're always going to use the X direction. So that's where it's IXX, is just to say I in the direction that we normally would use the beam. Sometimes you might have to turn the beam around for whatever reason. And also for columns it comes into it. Okay, so they've given us that value of 5.26 times 10 to the 6 millimeters. Okay, so we've got our information, we're happy with all that. Now let's see what we need to do. We need to find F, right? We need to find F. So what we could do is we could just put the formula in now, right? What we know, they've given us sigma B, right? They've given us the bending stress. The maximum bending stress can't exceed 65 megapascals. We'll assume that's a factor down, right? So maybe half of what the actual material can allow. So what I'm going to say is we'll just write all that formula in. So sigma B equals mi over I, which means that 65 times m, which we're going to say is FL on 4, times I, which is 60, over 5, 2 times 10 to the 6. Okay, so what we need to do now is we need to start converting things, right? So what we're going to do is we're going to say, well, let's put this over here. So we've got 65 times 5.2 times 10 to the 6 equals 60 FL on 4. So to get rid of the 4, we multiply that over here. Okay, so then to get rid of the 60, we divide both sides by 60. So this side divided by 60 equals FL. And then to get rid of the L, well, we can substitute in the L, right? We know the L is 6 meters or 6,000 millimeters, because we want to use millimeters for all our calculations, yeah? So what do we get there? If we then have to divide both sides by 60, yeah? So what I'm going to do there, I'll just write that, okay? Going to divide, so 4 times 65 times 5.26 times 10 to the 6 divided by 60 times 6,000 equals F. Okay, so F equals, I'm just going to put all that in the calculator. 4 times 65 times 5.24 10 to the 6 divided by brackets 60 times 6,000 close brackets equals a grand total of 3784. Now what unit will that be?
Newtons meters.
Newtons. It's a force. Forces are measured in newtons. Moments are measured in newton meters. Yeah, that's the answer I get. I'm just going to check to see if I'm wrong, because that would be embarrassing. Question 56. Yeah, close enough. Okay. We're now going to do 59. And once again, okay, well, let's have a look. I'm going to clear this part off so I can just use this space. You know what, I'll just move over. Okay, sigma b equals my times y, m times y over I. My over I is how I've always learned to say. Okay, so what we need to then know is what's m. M, in this case, we're allowed to use f times L on 4. Right, we're allowed to do that. Why? Because it's simple and symmetrical. Otherwise, we wouldn't be allowed to use that. We'd have to use a bending moment diagram. We haven't learned about that yet, so let's keep this show on the road. Okay, so what we're going to do is we're going to say F equals 10, but it's 10,000, yeah, it's in kilonewton meters, right? So we can for the moment we'll just write 10 kN, right? And what's our L? L is in meters, 8 meters, and again we don't really like meters, but we're going to do all our conversions back later. Okay, and then we have y. What's the value for y? Well, this question has asked us to find the tension, right? To find the compressive force. Now, I said there was a minor criticism here, which is that I think that this value here, the distance to the neutral axis from the top, would be much smaller. I think the distance from the neutral axis to the top would probably be half that distance. But I've got to go with what's in the question. I can't change that bit. So what I've got here is I've got two values of y. I can have y equals 120, or the opposite, which is y equals 140, right? Does that make sense? I'll make that clearer. Y equals 260 minus 120 equals 140. But there's two values for y. I have this one here, which is measured from the neutral axis to the top. Is the top in tension or compression? Compression. And I have the bottom one, the bottom one is, yeah, that one there. And this one here is yt. Now, as a rule, when we're designing for bending, we care about the one, if these y values are different, we are usually concerned about the one that is the bigger value. The value that is bigger is going to give you the fail case more often, right? So there's a video of me going, big Y! Right? So whenever we're not sure, probably better to go for big Y. In this case, the question has specifically said we need to use YT. They've said find the tension. Now, there's plenty of students who look at this question and say, but there's no tension in this thing here. It's in bending. It's not being squeezed, it's being bent. But you guys will know better. You'll know that when something is being bent, bending creates a combination of tension on one side and compression on the other. Yeah? We good? Okay, so that's the value we're going to use. We're going to use that value there. And then what we have now is MFL. Okay, so we need I. An I has been given. It's up the top, but I'll write it up again. I equals 110 times 10 to the 6 millimeters 4. Okay, now that I've got that information, let's just do this part here. M equals FL on 4, which is, I can write that down. M equals FL on 4, which equals 10 times 8 divided by 4. Okay, well, it's going to be 2, so it's going to be equal to 20. M equals 20 kilonewton meters. We don't like to use kilonewton meters. Right, when you see kilonewton meters, think, okay, I've got my kilonewton meters, now I need to convert it. How many newtons are there? There's 1,000 newtons in a kilonewton. How many millimeters are there in a meter? Another 1,000. 1,000 times 1,000 is 1,000,000. Yeah? 10 to the 3 times 10 to the 3 gives us 10 to the 6. So what we have is M equals 20 times 10 to the 6 Newton millimeters. Now we should be excited about that because this 10 to the 6 and that 10 to the 6, they're like, high five, because they're both going to cancel out. So what we have now is we're going to go back to our formula. Sigma B, right, equals 20 times 10 to the 6 times, we're using, in this case, it happens to be big Y, but they have told us to use YT, the tension, right? 140 divided by 110 times 10 to the 6. High five! Right, so we now have 280 divided by 110. The answer is going to be about 300, I guess, something like that. sigma B equals, let's go to the calculator. $25. Wait, way less than I thought. Anyway, 25.45 megapascals, right? Because we used grease units, we used millimeters, and we used the answer to come out in megapascals. And yeah, we're happy with that answer. That's the answer they had there. We go together like megapascals and millimeters squared. Okay, so that's 2 bending questions for you today.